do I need to share my screen? So, okay, great. Can everyone hear me all right? Yeah, sweet. Well, yeah, I know that I'm the last talk before lunch and also a free afternoon, so I'll try and be quick. My name is Sebastian Monzon. I'm a grad student at Yale University working with Frank Van den Bosch, and today I'm going to be talking about accreted stellar halos as probes of cosmological merger histories. So we all know that galaxy formation proceeds hierarchically, which means that the small galaxies form first and then coalesce and merge to form larger galaxies. And a good way of thinking about this is the so-called dark matter merger tree, which I'm showing here, where you're basically detailing the mass accretion history of some galaxy that you care about, often called the main progenitor. So in a simulation, that would be, for example, this central dark matter halo. This is a snapshot from the Aquarius simulation for a 10 to the 12 Milky Way mass host. And all this other substructure that you see here is the accreted component. So what does that accreted component actually look like? Well, this is obviously dark matter. So let's go to some Hydra simulation. This is from the Auriga suite, showing, again, a 10 to the 12 host, 6 different 10 to the 12 hosts, actually. And what they've done in this analysis is actually separate the stars that were accreted onto the main progenitor based on their morphology. So at the top panel, we have what would be called like intact or surviving satellites, and you could look for stream-like objects, and then also this kind of phase-mixed, diffuse extended component. And for the rest of the talk, I'll call all of this stuff accreted stellar halo, or ASH. But why do we care about it? In the Milky Way, it's been measured to be roughly 1% of the total stellar mass in the zero radius, so not very much. Why should we care? A couple of reasons, and maybe I shouldn't spend too much time here, but the first is galactic archaeology, which is the idea that you can use positions and velocities of stellar halo stars to reconstruct merger events. So this is how we found the Gaia Enceladus sausage, and there's been this interesting discovery of a break in the stellar density profile. You can also use the stellar halo to think about near-field cosmology. So, as long as metallicity is kind of a proxy for age, you can think about studying the earliest generations of stars, or these kind of POP3 stars, by observing them in the stellar halo, potentially. You can also think about the satellite abundances and how they might change for different reionization models. And so being able to accurately get a handle on how many systems are accreted onto your progenitor is really important for that type of analysis. But what I care about is actually dark matter inference. The standard kind of, game that people are talking about nowadays is this idea of trying to use gaps in stellar streams to infer dark matter masses, or kind of non-luminous dark matter masses. The idea here being that these very pristine structures can be perturbed by a lot of different things, but potentially a non-luminous dark matter subhalo. It's also really interesting that the progenitors of Milky Way mass galaxies lie in this mass scale where, because they have such shallow potential wells, baryonic feedback can potentially change their inner density slopes, from cusp to core. And that, of course, has an impact on how resilient they are to tides once they actually fall in and are evolved within the potential of their host. But today, what I care about is this idea of using the present-day accreted stellar halo mass to back out the formation time of the dark matter. And so this is work that's typically done using hydrodynamic simulations, or sometimes n-body simulations with particle tagging techniques kind of pasted on top. And that's what I'm showing here from Ray and Starkenberg. They're showing the accreted stellar halo component within 20 kiloparsecs. You can see that it has some interesting kind of, it moves around in this space based on when the dark matter halo formed. Okay, so I think it's also important to talk about the fact that the formation of the accreted stellar halo is a very stochastic process. And I'm going to talk about 4 main sources of stochasticity. The first one I don't think I'll have time to actually show plots for, but the idea is that if you look at, this is one of those particle tagging technique papers. If you look at 6 different Milky Way mass stellar halos, these are only stars that were ever accreted, so none of these stars are in situ stars. they all look very different, and that's partially because they have different mass accretion histories, but it's also partially just because the final fate of these satellites, whether they become a tidal feature like a stellar stream or phase mix, depends on their orbit. And so this is a very stochastic thing just to begin with. The other one, which I definitely will talk about, is that even at fixed halo mass, there's significant variance just because they have different mass accretion histories. That's the whole point of trying to infer Z50 or something like that from the present-day stellar mass. So that would be comparing panels C and D, where they almost have identical host halo masses, just different mass accretion histories. And you can already tell that panel D is a lot more massive. Also, like basically everything else in galaxy formation, the accreted stellar halo should scale with halo mass. Right? So you might expect, well, you don't. It's predicted that more massive halos have more substructure, and that substructure is also more massive. And so if the accreted stellar halo is nothing more than the disrupted remnants of that substructure, it should scale with halo mass. And then finally, I definitely won't have time to talk about it, the low mass end of the stellar halo mass relation is very uncertain. So this is work that I was presenting last year, but the actual slope of the stellar halo mass relation is uncertain. And more than that, the scatter can be potentially large at the low mass end, which is just another form of stochasticity that we really ought to take into account when we're trying to do this inference. Okay, so given all these sources of stochasticity, what can we learn about a galaxy's dark matter accretion history from this accreted stellar halo component? I'm doing this work with SatGen, and I'm not going to spend any time talking about it because we already had Fangzhu and Jay Schwan gave, I think, a little bit of introduction. The point is that SatGen is a fast, flexible model that's perfect for exploring parameter space and getting a good handle on halo-to-halo variance because it's built on extended pressure sector theory. So let's just dive right into the methods. So what do we do with the satellites? Well, each subhalo is given a stellar mass, or a satellite stellar mass, drawn from, right now we're just using Universe Machine's empirical stellar halo mass relation. So this is Peter Baruzzi's 2019 Universe Machine. We initialize the orbits of the satellite subhalo system using dark matter idealized simulations, dark matter only idealized simulations. So we basically just draw a position and a velocity for each of the satellites. And then we model the evolution, so how many stars are lost, based on a tidal track from Rafa Irani's 2018 paper, assuming that they all have initial NFW cuspy density profiles. So the satellite can do one of three things. The first is survive. So we define surviving or disruption based on the bound fraction of dark matter mass, not the bound fraction of stars. And so even if a dark matter halo, so the disruption criteria is a dark matter halo can't lose more than 99.99% of its initial mass. And so if it doesn't, it survives. And some stars may be lost depending on the tidal track, but oftentimes these things hold on to their stars, again because they have NFW profiles to begin with. But if it does happen to fall below that threshold, then all of its stars would be what we would consider the accreted stellar halo component. And then also we account for mergers based on the position and velocities of the satellite subhalo systems with respect to their parents. So that would basically be kind of this ex situ component of, for example, the central galaxy would be some fraction of the progenitor galaxy minus whatever's thrown up escapes into the accreted stellar halo. So that's the three things that a satellite can do in our model. Three fates. So what does this actually look like? So here's just some visualization. Again, these merger trees detail different mass accretion histories. So I just have 4 different merger trees that SatGen's given me. The red dot here on the bottom is the same exact host halo mass, 10 to the 12. And the color scheme is the different rank order of the subhalo. So a first order subhalo would be blue, purple would be second order, so on and so forth. And so once I have this mass accretion history, I can just kind of press play, and you'll see that the little red circle here is the virial radius of the host. It grows as a function of time. And each of these particles are the positions of the satellite subhalo systems within the potential. So I can't tell you where the stars will end up because I'm not actually modeling any stars. All I can tell you is how many stars are lost to the accreted stellar halo based on this kind of very simplistic point particle orbit integration. Okay, so that's the satellites. What about the central galaxy? Again, we look at, we turn to the Universe Machine. In particular, we use an in situ star formation rate prescription that's based on Vmax. So for the same mass accretion histories that I was showing before, I can translate that to Vmax, convert that to star formation rate, and integrate it as a function of time. And that's what I'm showing here as this central galaxy component. It turns out that because this model has an increased star formation rate at cosmic noon, earlier forming galaxies tend to have slightly higher stellar masses than later forming galaxies. And also that ex situ component that I was talking about in the merger criteria is very much subdominant to this in situ component. Okay, so let's talk about that second source of stochasticity, that halo-to-halo variance, or different mass accretion histories. So again, I'm just showing those same four merger trees, how the central galaxy grows, and now I can actually show you how the accreted stellar halo grows as a function of time. Here on these axes, I'm always going to normalize it by the central stellar mass. And indeed, you see that different merger histories produce different accreted stellar halos at z equals 0, and our model is reasonably consistent with estimates from the Milky Way. There's, of course, pretty large error bars on here that I haven't put on. And it's not necessarily clear, at least from these four data points, if there's a trend with Z50 or the accretion history of the dark matter. Okay, let's talk about the third source of stochasticity. Last year, maybe some of you will recognize this plot. I was talking about these three different merger tree samples that I created. The first of which is 10,000 merger trees, all centered exactly. It's a delta function at 10 to the 12 in host halo mass. And then I've kind of just widened that distribution incrementally to create the S15 and S30 sample. Here the idea is to allow more and more host halo mass mixing and see how that kind of changes both the subhalo mass functions, the progenitors that accrete onto the host, but also how that changes the mass accretion histories. Right? So if I then take these 4 little or 5 little points and put them in the context of the 30,000 other merger trees that I have in the sample, this is what it looks like. And so from green to orange to red, you can see that we're getting wider and wider in terms of the central galaxy mass, but not necessarily in terms of this accreted stellar halo component, and specifically because I'm normalizing it by that central stellar mass. We can also look at the distribution of a formation time like Z50 and see how that correlates with the accreted stellar halo. And indeed, we see for all 3 samples, even the ones that have more mass mixing, a very strong negative correlation, which means that galaxies that form earlier tend to have less massive accreted stellar halos than galaxies that form later. And what's kind of a fun little exercise is asking whether Z50 is the formation time that maximizes these correlations. And it looks like Z50 actually does a pretty good job, maybe slightly below that. But what I'm going to do for the rest of the talk is just use Z50 because it happens to also be a really high correlation with the central stellar mass. Of course, by construction, that it scales with Vmax. Okay, so let's play this game of inference. I don't think I have very much time left. We're going to play the game using random forest regression. So the idea here is that, and I have results in stars because this is all very preliminary. But the idea is that you can train a random forest regression model on data, and then basically ask it to give you what it thinks. So you train it based on features, or what's often called features in the literature, and then you ask it for a target variable. So here the features would be, for example, the central stellar mass, the accreted stellar halo component, the total stellar mass in satellites, and the target here, the thing I care about, would be Z50. So for each of the samples, I have 10,000 merger trees. I've broken off 8,000 of them to train the model, and then I can go and ask how well does it do on the remaining 2,000. And so that's what I'm showing here, predicted versus true for each of the 3 samples. That R-squared score is basically a score for how well it was calibrated during the training. So an R-squared score of 1 is like a perfect score. And you can see that R-squared goes down as you include more and more host halo mass mixing. And also the residuals here become more and more biased as you include more and more host halo mass mixing. But what's interesting about random forest regression, I think what's exciting about it, is that it can also tell you which of the features have the most information content when it actually, in terms of constructing the decision trees that go into the algorithm. And so for the S0 sample, you can see by and large M central dominates the information content. And as soon as you start including more and more host halo mass mixing, these 2 other components have to kind of overcompensate. Now that doesn't necessarily mean that you're getting better answers, right? As you can see by the R-squared score and the residuals. But it does mean that M central is now kind of less indicative of a formation time. Okay, so there's plenty of other games that I can play with, and believe me, that's exactly what I'm doing, trying to find the best way to ask this question of inferring the Z formation based on these different components. But for now, I'll just leave you with my conclusions, which is that the stellar halo holds a wealth of information. We've developed a model to simulate the growth of the stellar halo that properly accounts for these different sources of stochasticity. And our model predictions show a strong correlation between Z50 and the accreted stellar halo, and we're going to be playing with random forest regression algorithms to test that. Thank you.
Questions?
Thank you. Very interesting talk. I was wondering if you have considered to consider another dark matter profile instead of Navarro-Frenka-White, and which do you think that it could be the impact on the results?
Yeah, it's a great question. So, like I mentioned, our assumption is that all of the subhalos start as initially cuspy NFW profiles, but Arani's, well, I don't know if I can click there. Arani's model actually has a calibration for, if they started as cusps. And it's not something that we've played with quite yet, mainly because the rest of our model also assumes NFW, so it's not just the tidal track that would need to change, it's also other parts of the model. But the idea is that cuspy profiles are a lot more resilient to tides. And so if you have a chord subhalo population, you might expect, they're much more capable of enriching the accreted stellar halo, maybe more efficiently, or So it should definitely make a difference, and it's something that we want to test for sure.
So two quick questions. One, did you include the central potential in the?
Yeah, good question.
And is that driving a lot of the trends, or does it not matter that much?
So I didn't actually. There's no disk potential in these runs of SatGen. It is something that we definitely can play with, but work that has been done in the past by some of Frank's previous students show that when you do include a disk potential, it actually doesn't really change that much in terms of the abundance of subhalos or the disruption, unless you're looking like really
in the
close
middle.
in
So the middle, I guess, is where the next piece was. Have you broken out the piece of the halo that's not phased mixed? Because I would think that would be the one that really correlates with stuff the most.
Yeah, so again, I can't really tell you where the stars end up because I'm not actually modeling the positions of these things. But what I could, in principle, do is tell you where the majority of their stars are lost, in the orbit of the satellite. And so backing that information out is kind of difficult given this toy model, but it's something that we would like to do.
Okay, so I guess that we should thank Sebastian.
Thank you.
And all the speakers of this session. And we can move on to the discussion section.
We've been just discussing the discussion session because I'm mindful that it is half an hour over, so that means we're 10 minutes past the end of our discussion and 10 minutes into our lunch break already. My stomach is having its own discussion session right now. I don't know about you, so we wanted to do a show of hands. Two options. One option, who would like to go and have lunch and talk with people and have no discussion session? Hands up. Okay, it's quite. The other option is, who would like to go and grab your lunch and come back in and have a discussion session? It's reasonable. Okay, we'll do that. And if you don't want to, it's okay. You can have your lunch out there. But go grab your lunch if you want a discussion session. We'll come back in here.
Just about the food. So there are a couple gluten-free options at the far end of the table. Don't take those if you're not gluten-free. And if you are, grab those. There are also a lot of vegetarian and vegan ones. There are 3 types, so grab what you need.
If I stand over here, will there be feedback? Oh, that's good. Is it all right? I'm sure it'll be all right. I'll just... Trying new microphone. It's a bit echoey. Is it a bit echoey? Trying this one. Oh, okay. Yeah, let's do 5 minutes. But I think we should ask them which question. We have so many questions here. Yeah. Yeah. Okay, thank you everyone who has come back in to have the discussion session with your box lunches. It's lucky that we had box lunches today. Thank you to the organisers for thinking of this. And now Andrew and I are going to